Hello everybody. In this video I will talk about the surface tension and the capillary effect. Both of these phenomena are very important in fluid mechanics, and yeah, let me actually first let's discuss some of the common observation related to these topics. So let's actually some of the common observations, or I would say some of the applications of these. So some of the observations related to surface tension, you must have noticed that the water drops from rain or dew hang with leaves. Okay, even though the water is much heavier, but they are still hanging with the leaves. So if this is your leaf, the water drops are actually hanging, and you know that it has a pretty high weight, but they are still hanging with the leaf. So another common observation is why we add soap to water when washing our clothes. Okay, or in the same way, why we heat up the water. Okay, and in fact we will see that if you are using a detergent, you actually don't need to heat up the water, but that is one of the applications of surface tension. But another example is, you must have noticed that needles or heavier objects actually some of heavier objects float on water even though they are heavier than water. And also insects, insects can walk on water. Another example actually is, this is an interesting example. It's to do with the jaundice test, jaundice test. So in a jaundice test, this is a medical condition. So basically by sprinkling sulfur on urine, so the idea is you have some urine, and then you sprinkle some sulfur. If the bile is there, if bile is in urine, then those sulfur actually will sink to the bottom, and you can find out if the person has the jaundice or not. So these are some of the observations, and in fact there are very many applications. And again, surface tension and capillary effect together, they actually have a lot of application. In fact, the plants also get their nutrients due to this capillary effect, which is a combination of which actually depends on the surface tension. But some of the observations, so let's actually look at it. Why do we have the surface tension? So in fact all these phenomena are, like what we discussed earlier, are due to surface tension. Okay, and the surface tension is represented with letter sigma, and it has the units of Newton per meter. So in other words, it's force per unit length. So sigma, which is the surface tension, is equals to force per unit length. And so let's see why there is a surface tension force. Okay, so let's suppose you have a fluid or liquid in this case. So you have a liquid and you have molecules inside this liquid, and if you look at this molecule over here, it will have the attractive forces from all the directions. So basically this molecule has attractive forces from all directions, and the attractive forces are balanced. Okay, so you have all balanced. I mean, so this one is I should say all attractive forces are balanced from each. So attractive forces are balanced from all directions. Okay, so let's take a look at another molecule that actually is on the surface. So if you have a molecule which you can pretty much take anywhere on the surface, so if this is the molecule, it has more attractive forces from these direction from this, but it does not have as much of a strong attractive force from the outside, which actually is air. So this molecule has an unbalanced force. Okay, so what it means is it is trying to be, I mean, it is being pulled more towards the liquid compared to like the force that it is experiencing from outside. So there is a net pull inwards, and that is why and again, so that is why the fluid tries to minimize its area, minimize its surface area, I would say. Okay, and then this attractive force basically acts as a thin layer, and it acts like a surface. So again, okay, so and this is the reason that actually if you have a fluid drop or a liquid drop, it tries to attain a spherical shape. Okay, so it tries to attain a spherical shape because if you think about it, all the molecules inside this I mean, so this is if you, so all the molecules, they basically try to come closer. Okay, so this is how like a drop, again, it's not like completely spherical but it tries to attain a spherical shape. Okay, so how can we actually calculate the surface tension force? A couple of ways you can do this. One very simple experiment is, and again I will talk about another one. One very simple experiment is you have a wire frame. Okay, so let's suppose you have a wire, like a thin wire, and then this is the height B of this, and let's suppose if you have a movable wire, okay, in between, so which actually this wire will be able to move this way or that way, and now you basically dip this inside a liquid solution, and by the time you take it out, and in fact mostly you can take a look at it like in a soap solution. You can pretty much do it for any liquid, but usually the soap is a little bit easier to see in this case. So when you take the you dip this into a soap solution, when you take it out, you will see that there will be a soap layer, and again, as I mentioned, the liquid has more attraction, so it will tries to minimize this area. So as this wire is movable, so it will try to pull it in this direction so that the area can be minimized and molecules get closer. But if we hold this in this position, so basically you have to apply a force F to hold it in to hold it steady, and this force can be calculated. Of course, you are holding it from one side and the wire is trying to push in the other way, so you can basically measure that force. So if I'm looking at this from the top view, okay, so if I'm looking at it from the top view, so basically you are applying a force F in this direction, and then you have a fluid layer in this direction and in this direction, which both of these are actually represented by sigmas. So you have two thin layers of this soap film, so this is represented by sigma and sigma. So I can write this as sigma, okay, so 2 sigma is equals to F over B. Again, the reason I'm writing this as F over B because this is the total force per unit length. So the total force per unit length, so F over B will give you the units of Newton meter. Okay, so F over B basically gives you the Newton meter, and then sigma is equals to F over 2B. Okay, so this basically gives you your surface tension force. And I mean, so you can find out what this force is, what this length is, and you can calculate your surface tension in terms of Newton meters. Another way, which is a very common experiment that people normally do, which is called a pendant. um, I think it's called yeah, pendant. I kind of forgot the name, but um, yeah, okay, so if I think about it, I will mention that. But the idea over there is you actually need a camera. Okay, so what happens is, if you have like a tube over here, and then you what I mean, so you will let the fluid drop basically fall down because of its own weight. So, and you are taking some pictures, and then you will see that, okay, after, so if this is the fluid drop, and after a while you can monitor, like, okay, if you look at it, you can find your, like, the radius of that circle and everything, and this will tell you what the weight of the drop would be. So if you find the weight and everything, so based on that you can find the surface tension. So I mean, a little bit more involved, but the idea is you have a weight, which is a force, and then again you can find out what the pinch off point is, and then I mean, and some fluid which actually has a lower surface tension basically will have a smaller size drop. And in fact, if you think about water, it will have a bigger drop compared to if you're talking about some alcohol or something. Okay, so alcohol has a smaller surface tension, water has a higher surface tension, so that is the reason you will see that water drop will be much bigger. I think it's a pendant, yeah, but yeah, okay. So that's how you will actually calculate your surface tension force. The next thing is, so let's actually take a look at for the case of a drop. Okay, so as I mentioned earlier, the surface of the drop tries to minimize. Okay, so minimize the area, and inside liquid is under pressure. And you can think about this as, like, if you have a sphere. Okay, so if this is your sphere, so now the idea is, because the fluid molecules are trying to squeeze inside, and as soon as you basically, because of the surface tension force, and the more they squeeze, the more this water, like the drop, will actually experience more pressure. So the pressure will build up because the thing actually is trying to compress it with the surface tension force. So now the fluid inside is also trying to push it outwards also. Okay, so if I look at half of the cross section of this droplet. Okay, so if this is the case, like this. Okay, so now on the surface, and of course this is a surface phenomena, so on the surface you actually have the surface tension force, which actually will be acting on the circumference, so which is 2 pi r, the circumference, times the sigma. So that is your surface tension force. And then again you have this pressure that will build inside this, and it will be acting on this whole cross-sectional area, and that will be pi r square times delta p of the drop. And again I will mention what delta p is, but in fact let's actually, these two forces have to be equal, so pi r square times delta p of the drop, where delta p of the drop actually is pi minus p out. So pi is the inside pressure and p out is the outside pressure. So inside pressure of the drop is pi, and the outside one is the p out, and the difference of those two is represented by this delta p. So I can find out what the pressure drop, the difference of the pressure drop from the inside to the outside is, which is p minus p out, is equals to, this cancels out with this, pi cancels out with this pi, so what we are left with is 2 sigma over R. So the pressure drop inside a droplet is given by this expression, and this is an important expression. If you think about it, the smaller the radius of the drop is, so radius is small, the more the pressure difference would be. So you have a smaller radius drop, and it will have a higher pressure difference from inside to the outside, as you can see over here. So this quantity does not change. The only thing that is changing the pressure, the Pi minus P out, is this R. Okay, so that is something I wanted to mention, that the smaller the drop would be, the bigger the pressure difference from inside to the outside. Okay, another thing is the surface tension changes. So surface tension varies. Surface tension varies greatly from substance to substance, and also it depends heavily on temperature. Okay, so it depends heavily on temperature. So in fact, let's look at some of the, so if I say I have a fluid, which actually is, so in this case I have water, and sigma, which is Newton per meter. So some of the values, so water at 0 degrees Celsius, the surface tension is 0.076. Water at 100 degrees Celsius, the surface tension is 0.059. Water at SAE oil 30 has a surface tension of 0.063. Mercury has a surface tension of 0.440. And again, why this thing depend quite a bit on the temperature, as we discussed about in an earlier video about viscosity. So the same idea applies over here. So let's suppose if you have a fluid, so this particle actually sees more attraction from inside because you have lot more molecules over here. But when you increase the temperature, so what happens is you will see lot more molecular movement over here. So molecules are moving, so they don't, so the cohesive force actually reduces as you increase the temperature because of the vibrational energies of the molecule. So as you increase the temperature, the cohesive bond, the cohesive forces decreases. Okay, so as you increase the temperature, so that's why as you increase the temperature, you basically increase the so as you increase the temperature, you basically lower your surface tension force. Okay, another thing is, if you want to decrease the surface tension of water, you basically add a detergent, and the detergent are also reduces the surface tension of water. And anything that reduces the surface tension of water, they actually are called surfactants. F-A-C-T-A-N-T-S. So anything that reduces the surface tension of water, actually it's also known as the surfactants. Okay, so why this thing is important? Why do we use surfactants? So let's actually take a look at a fabric. So if I'm not using a microscope, but let's look at some of the threads of those. So if this is like some fabric that we have, and we want to basically wash this, so what happens is, if I'm using water, like a cold water, as I mentioned earlier, it will have a higher surface tension, and at 0 degrees Celsius the water surface tension is 0.076. So the effect of this would be that the drop that the water will make will actually be much bigger, because it can hold a much, because it has a higher surface tension, so it will be able to make a bigger droplet of water. Okay, so now when you, and again, I mean, this is an exaggerated view, but if this is where the water has to go in and actually wash the cloth, so if the droplet is this big, so then this water won't be able to go inside these gaps. So what you normally do, you basically add a surfactant or detergent which reduces the surface tension force, so that reduces the size of those droplets, and those droplets are much easier to go inside this fabric and be able to wash. So, or you basically increase the temperature, as I mentioned. If you make it 100, so the surface tension force decreases to 0.059, and even with the hot water you are able to create a smaller droplets, and those can also go and wash this clothes. So the idea is, even if you are using a cold water and you are using a surfactant, so that is fine. You don't have to always heat up the water, because the surfactant reduces the surface tension and you will be able to create smaller droplets. So I leave that up to you. Next time you are washing your clothes, you will think about it, why you can actually do it with just hot water, or you can use a surfactant to reduce the surface tension force. Okay, so the idea is, again, and this is, materials are classified as hydrophobic, PHOBIC, or hydrophilic, based on their affinity for water. So based on their likeness for water. So if the surfaces, if water basically wets a surface, then it's hydrophilic. If the water does not wet a surface, then it's hydrophobic. And again, both have their own advantages. So for example, you want to, so let's actually take a look at, so if you have a soap basically is a hydrophilic, because water will I mean, so the water droplet actually looks something like this on a soap bar, because it will reduce its surface tension and everything. But again, I'm gonna create an angle which I'm describing as so this angle I'm calling as theta, or like sometimes it's also called phi, is called the contact angle. And the things or the liquids that actually wets the surface, the actually phi has to be less than 90 degrees. So phi is less, actually, yeah, so phi is less than 90 degrees, and only then it will wet the surface. Okay, so the opposite of that is, so let's suppose if I have another surface which we can make hydrophobic, so the water does not basically wet that surface, and the water droplet will sit something like this. So this is a water droplet, and again, normal to this edge, I will create this angle, I mean I will create this line, and this angle actually is, again, it's phi, and if the phi is greater than 90 degrees, so it will not wet the surface. And this thing actually is called a contact angle again. But anytime you go and wash your car, you normally wax it, because you want to make the surface hydrophobic, so that the water does not stick to that surface and it basically rolls off. So if you wax the surface, so wax surfaces basically acts as hydrophobic surfaces. Another application where this is commonly used is the firefighter helmets. They are also made hydrophobic, because anytime a firefighter basically goes into a place where there is steam and all that, you don't want that the firefighter helmet, like the covering, you don't want it to be soggy and all that. So you want basically the water to don't stick with the surface, and in fact create drops and just roll down from that from the glass. So basically you can make surfaces hydrophobic by either waxing those, by either putting some oil on those, and so on. Okay, so this was the idea behind the surface tension. The next is the capillary effect, and which also borrows some things from the surface tension. But let's actually look at what is a capillary effect. So as you will notice, water will rise next to the walls of glass, okay, and mercury will drop. Okay, so this is some observation. You will notice that if I have a big beaker, and this is water, you will notice that the water will actually bulge from on the side, and if I have to make a contact angle, I have to show that. You will notice that this is the contact angle phi over here, and in this case phi actually is less than 90 because it will wet the surface. But in the opposite case, if I have the same beaker and it's made out of glass, so again this is made out of glass, this is also glass, and now we actually have mercury in this. Okay, so this is mercury. And again, why this happens? The reason this happens is because the molecular attraction between the molecules of water with the glass is stronger, so that's why the water tries to stick with the glass. But the molecular attraction or the cohesive forces inside the mercury is more than the adhesive forces, which is between two dissimilar substances. So the cohesive forces are more stronger compared to the adhesive forces, but in this case you still have very strong cohesive forces, but you also have very strong adhesive forces between the water and the glass. Okay, so this is wetting fluid, and this is non-wetting fluid, and in fact I can extend this out and you will see that this is your contact angle, which actually is greater than 90 degrees, so that's why it's a non-wetting fluid for that specific material. I mean, for some other material it could be, but for the glass, mercury is a non-wetting because the contact angle is more than 90 degrees. Okay, so what is a capillary effect? So now, with the same idea, keeping in mind that water rises its level as it gets in touch with the glass, but now if I take a small capillary, so if this is like a small capillary thing, and I basically insert this inside the in water, so water basically rises from the sides and all this. But you will notice that again this has nothing to do with how we measure the pressure. So this is open from the this is open, so it's not that there's a vacuum and that the water is trying to push in. This is how the barometer works, which we will see in a later lecture. But right now so as soon as you have a smaller diameter tube, the water will start to rise up, okay, and it will keep on rising up and up and up, and to a certain point. So let's suppose it comes all the way up till this point. Okay, so why does the water rises up? Again, as you will notice, water actually has a very strong it has a very strong adhesive force with this glass. So what happens is, if I let me actually extend this out, so if this is okay, so in fact let me show you here. So now water tries to basically stick with the glass, and again more water molecules wants to stick with the glass. Okay, so as soon as this gets in touch, so these water molecules get in touch with the glass, the surface tension force actually pulls this water up, okay, and you pull a little bit more water up, then more water wants to stick with the glass, and then it just keeps on increasing and increasing until a point reaches when the surface tension force cannot overcome the weight of the liquid. Okay, so this is an important concept, that the surface tension force is pulling the water up, but to a certain extent, then after a while the weight of the fluid will basically counter the surface tension force, and after that basically you cannot pull any more water. Okay, so why that did not happen in an earlier case? Because if you think about it over here, it has to actually pull a lot more quantity of water, so that's why there will be only slightly only of this much of a bulge. But if you have less amount of water here, then even this will go up. So the idea is that the surface tension force basically pulls the water up, and inside a small capillary which has a very small diameter, it's much easier for the surface tension force to basically pull the water up. Okay, so again, the surface tension force can only hold the water, so the weight will be countered by the surface tension force. So if I basically look at this right now, so I'm gonna draw the force balance for this. So this is how it looks like. So this is the amount of water or the liquid we have, and this is the weight of the liquid. And so weight of the liquid is actually pi r square, so pi r square h. Okay, and so this is the volume of that times the gamma, which is again rho times g. Okay, so which is rho times g, which gives me the weight of the liquid. And then from the surface over here, we actually have that those two as so this is a contact angle, this is contact angle, but this is actually a circular shape. So the surface tension force, which actually will be in this case, it's happening all across the like the circumference. Okay, so the surface tension force actually is 2 pi r 2 pi r sigma cosine of cosine of phi. Okay, so this is your surface tension force. Okay, so in other words, this is basically balancing this thing, the weight over here. So now if I write this out, so it will be pi r square h rho g is equals to 2 pi r 2 pi r sigma time cosine of phi. Okay, so pi cancels out with this pi, r cancels out with this r square, and what else do we have? Okay, so that's pretty much. So in fact, if we want to find out how much is the height of that rise is, so that will be given by this expression over here. So h is equals to 2 sigma cosine phi over we have r rho g. Okay, so that will tell us how much the height of that fluid column would be. And again, I just wanted to point this out, that the surface tension force can only hold water of a certain weight. Okay, so the surface tension is, so the weight of the water will always be the same. That's the maximum. But if I reduce my diameter, if I reduce my radius of the tube, the water column height will keep on increasing, because if you notice in this equation, basically 2 is constant. This sigma, which is the surface tension force at certain temperature, this is also constant. The contact angle is a constant between a fluid and a material. Acceleration due to gravity is constant. The density of the fluid is constant. So the only thing that basically changes the height of that fluid column is this r, which is the radius of the tube. So the smaller the tube you will make, the higher the the fluid rise would be inside the tube. So again, this is an important concept, especially when you're using some sort of a barometer or a manometer. You have to make sure that you're not using a very small diameter tube, because due to the surface tension effect, or like the capillary effect, you might have an erroneous reading. So it's recommended to at least have I think 1 to 2 centimeter diameter tube, so that the surface tension, so the capillary effects are basically neglected. Okay, so again, this is an important concept. I just want to mention that again. that the surface tension force can only hold as much of amount of water. Okay, so the weight is basically countered by the surface tension force. So if I reduce my radius, so the height of the fluid column will increase. And let me actually um, do an example. So I will do an example over here. Okay, so here's an example for surface tension force, and as I was mentioning to you earlier, that the plants also get their nutrients using this capillary effect. So this example I took it from Fluid Mechanics Fundamentals and Applications by Singel. So what it says is the nutrients dissolved in water are carried to upper parts of the plant. So determine the height to which water solution rises due to the capillary effect when the contact angle is 15 degrees, diameter of the tube is 0.005 millimeter, and the surface tension at 20 degrees Celsius is 0.073 Newton per meter. So again, as you will notice that the surface tension is given at some temperature. So if I look at this plant, okay, so you have a plant, lot of it actually is inside because that's how it's getting its nutrients from. So you have like small capillaries over there, which basically sucks those basically takes the fluid all the way up into the trees, and that's how basically trees get there. So what we want to find out to determine the height to which the water solution rises. Again, so we have developed that equation in the previous slide. As you can notice, this tells us how high the fluid can rise based on the radius of that of that tube in this case. So if I have this which is H is equals to 2 sigma cosine of phi divided by rho g r. Okay, so rho g r, and now what we do have in this case is, okay, so this is 2.073 Newton per meter cosine of 15 degrees divided by 1000 kg per meter cube, and again the unit, to make sure the units are consistent, 9.81 meters per second square, and 2.5 into 10 raised to power minus 6 meters, because everything was in millimeters, so I converted that into this, and then I will multiply that with a factor to basically make unit consistent. So 1 kg per meters 1 kg meter per second square, which is also same as 1 Newton, and just to cancel this Newton force, and then kg cancels with this, second square cancels with that. So in the end, and then we have meter that cancels with this meter, and then this meter multiplies together and it cancels out with this. So in the end we are only left with the meter as a height, so which will be 5.75 meters. Okay, so this, by this height the fluid actually will be risen from the bottom to the top of the tree. Alright, so that's pretty much what I wanted to say about the surface tension force, or the surface tension and the capillary effect. I will see you in the next video. Alright, bye.